Euler's method. Objectives. By the end of this lesson, you should be able to use Euler's method to approximate a value on a particular solution curve given a differential equation and an initial condition. Before we begin, let's talk about what we can do so far given a differential equation of the form dy dx equals f of x comma y. So in other words, we're given a derivative that might have x's and y's in it. So far, we can draw the corresponding slope field. We can find the general solution if it's a separable differential equation. So we can find the general solution with a plus c. We can find the particular solution with no plus c if we're given an initial condition, again, if it's a separable differential equation. And with a differential equation, we can find an equation of a tangent line as long as we're given a coordinate point, so an x and a y. So what Euler's method is going to add to this is it's going to allow us to numerically approximate values on a particular solution curve given a differential equation with an initial condition. And it's going to involve using tangent line approximations that hug the solution curve. So we're going to need to be given a differential equation and an initial condition, and we're going to approximate other values on that particular solution. Let's start by considering this differential equation dy dx equals 1 plus y with this initial condition y of 0 equals 1. So I'm going to stop right there. We've been given a differential equation, so I can plot its slope field, which is this image off to the left. If it's separable, I can find a general solution. And it is separable. I can divide by the 1 plus y, so dy over 1 plus y, and then multiply by the dx differential. So I can separate the y's from the x's, I can integrate, I can find a general solution, and because I'm given an initial condition of y of 0 equals 1, I can find a particular solution that passes through this point. So now let's see what the problem is asking us. We're being asked to approximate y of 3 without solving the differential equation. So approximate y of 3, meaning there's a specific value for y of 3. And I want to clarify that I can find y of 3 exactly, because solving this differential equation would give me y equals some f of x, which of course I could just substitute 3 in and find y of 3 exactly. But the point is, I want to approximate y of 3 without actually going through the process of solving the differential equation. And in a lot of the cases we're going to look at, we're not going to be able to separate the variables, so these are not even, it's not even going to be an option to find the answer exactly. In this one it is, but in general it might not be. So we want to approximate y of 3. So let's think about what we can do. So we said we can draw its slope field, perfect. We want to consider the particular solution that goes through 0, 1. So because this is a slope field, if I want to pass through 0, 1, this image on the right is a sketch of what the particular solution curve is going to look like that goes through 0, 1. So this curve is y equals f of x. And if I'm being asked to approximate y of 3, well, 3 on the x-axis is right here, so I want to approximate the function value that's way up here on this curve. So this curve goes up and up and up and up. So I'm trying to find f of 3. So we'll say that it's right there. It's a little off center, but that's the value we're trying to approximate without actually solving this differential equation. Alright, so one of the other things we said we could do, given a differential equation and a point on the graph, is find an equation of a tangent line. So we do have a point. This is the point 0, 1. So I can find the equation of a tangent line right at 0, 1 to this particular curve. So I can find the equation of this line right here. So I can find the equation of this tangent line. Now, if I used this tangent line as a linear approximation, I'm not going to get a very good answer. So if I could see this line continues, if I try to figure out what the approximation is if I substitute 3 into this line, notice how far off I am from the actual y value that's the solution. So it's not a very good approximation. So what we want to do is use Euler's method to create sort of a series of line segments that are going to hug the curve. And this first linear approximation is going to be the first line that we consider. Alright, so we saw a generalization of what we're trying to do, so now let's get a little more specific with this example. So we can create a tangent line at 0, 1, and the specific slope is going to be found by substituting 0, 1 into dy dx. So dy dx at 0, 1 equals 2. So off to the corner I'm going to write down what dy dx was just as a reminder. So dy dx was 1 plus y. So substituting 1 into this y value, 1 plus 1 is 2. So here's my slope and here's my point. So that means that this first tangent line that passes through 0, 1 has an equation given by y minus 1, so I'm using this coordinate point, equals 2, the slope, times x minus 0. So here I can just go ahead and add the 1 over, so y equals 2x plus 1 is my first tangent line. So y equals 2x plus 1 is the tangent line that goes through 0, 1, and we're only going to consider it between x values of 0 and 1. So now I can figure out what coordinate point my tangent line goes through at 1. So at 1, this coordinate point passes through 1, 3. So I can substitute 1 into this tangent line. So y of 1, so 2 times 1 plus 1 equals 3, which if we drew it carefully we can see on the graph. So in other words, I have a coordinate point, another one, 1, 3. So if I want to create another tangent line, I'm going to need another slope. So to find the slope, I'm going to go back to my original differential equation. But now I'm going to use this coordinate point on my first tangent line approximation. So here's my coordinate point. My slope that's going to correspond to 1, 3. So dy dx corresponding to 1, 3 now is going to be 1 plus 3. So my slope here is going to be 4. So if I wanted to write the equation of this new tangent line, I'm going to have y minus 3 equals 4 times the quantity x minus 1. So here I have 4x minus 4, and then I'll add the 3 to the other side. So I have 4x minus 1. So this is now the equation of this second tangent line that now we can sort of see hugs the curve more than if I were to have just continued on with the original tangent line approximation. So this green line segment here comes from the line 4x minus 1, but we're only considering it between 1 and 2. So we can continue this process. We've gone from 0 to 1, now 1 to 2, so we can continue this process from 2 to 3. So we can use this coordinate point up here at 7. So 2, 7 is going to be our next coordinate point. And again, to find our slope, we're going to use our original dy dx over here. So this process, the way that I've written it, has gotten a little bit lengthy. So what we're going to do is now just come up with a concise way of doing this. And we arbitrarily chose to use a distance of 1 unit. So we chose the next coordinate point 1 unit away from 0 and then 1 unit away from 1. But we're going to be able to choose any distance we want, and the smaller distance we choose, the better we're going to hug this original solution curve. Before we formalize the process, here's one graphical example of a solution curve and then us creating a sequence of tangent lines that in this example are closer together than the previous example. So in the last one we went from 0 to 1, and that every distance apart between our tangent lines was a unit of 1, but now we can see that if we make that distance smaller, then we're going to hug the curve even closer. So we're going to have a better and better approximation for a value specifically on the solution curve without actually finding the equation for the solution curve. Moving on. Alright, let's look at a concrete example here. So we have let dy dx equal 1 plus y with this initial condition y of 0 equals 1. We want to use Euler's method with a step size of delta x equals 0.1 to approximate the function y at 0.5. So when I see that I have to use Euler's method, this is a nice little table, that this first row across, something that you want to memorize. I mean, basically what it comes down to is this is just a methodology, right? Euler's method. We're just going to keep going through the same type of repetitions over and over again. So it's nice if I have a clear way to see what I'm doing. So our initial condition, y of 0 equals 1, translates to my first x value is 0, and my first y value is 1. And I'm going to call that y old because what I'm trying to do is I'm trying to look for an approximation for y of 0.5. So I have to get from 0 to 0.5. So I'm going to have a new y value every time that I'm trying to generate. So I have 0 and 1. And then delta x comes next, so that's the how much I'm going up or down potentially every time to get to the next x value. So delta x is a tenth, right? So that means that I can fill out this column automatically. So delta x is always 0.1, and that means that the change in x goes up 0.1 every time. So it goes up because I'm trying to get from 0 to a half. So that's why I have to go up a tenth every single time. So 0, 0.1, 0.2, 0.3, 0.4, and 0.5, that's where I'm going to stop. So I'm in search ultimately of y of 0.5. I'm in search of this number at the end. And then dy dx is going to change every time. It's going to depend on whatever the equation is for dy dx and whatever my corresponding values are. So dy dx is dependent upon only y values, so 1 plus y. So this 2 right here, this first row has been filled in. Let's just analyze where it's coming from. I'm plugging in my y old from this row. So 1 plus 1 gave me 2. And then the question becomes, what do I do with these values? So here's how I'm finding my y new, that's the last value, is I'm taking my y old, which was 1, and I'm adding it to my dy dx, my slope, times my change in x. So that was 0.1. So this is really just y equals y1 plus m times x minus x1. That's exactly what this formula is. So it's just, the original value plus the slope times the change in x to get me to a y new every time so that I'm hugging that curve and getting a better approximation for y of 0.5 if I move with these really small step sizes of a tenth every time. So in other words, I'm going to create this row. I'm going to fill in these pieces. I'm going to start with what I know. So all I would have put to begin with is I could fill this out right away. I can go up by a tenth every time. Delta x doesn't change. It is a tenth every time. I can fill in my first y old value, and then I'm going to find my first slope, and I'm multiplying these two values, right, delta x and dy dx, and I'm adding that to my y old. So I can see 1 plus a tenth times 2 is 1.2. So that's my new y value. That's an approximation for y of 0.1. So that's what goes into, now that's an old value because I'm going to keep going. I'm going to keep doing the same repetition. So 1.2 is now an approximation for y of 0.1, and I'm going to use that to find my next dy dx, which is only dependent upon y. So 1 plus 1.2, right, 1 plus 1.2 is 2.2. So then what's going to go right here, is my y old, so that's 1.2 plus 0.1 times 2.2. And that's going to give me 1.42. And now that is my 1.42 is my y old in this next row because I'm going to keep going, right? So now add, multiply is the operations that are happening. I need to find my new slope, my new dy dx, which is dependent upon my 1.42 that I just found, so that means it's 2.42. And I'm going to skip writing this out and just tell you what the value is. And I was actually obtaining these values in my calculator. The idea is that you're not supposed to use a calculator for this, but you could, right? It's just a lot of tedious arithmetic. But the bottom line is you could do this with a calculator, and you're getting a pretty good approximation. So now 1.662 goes here. My new slope would then be 2.662, right? I'm adding 1 every time. My new y value is 1.9282, which then becomes my y old for the next row. And then so my new slope is 2.9282. And then this is 2.22102, which is ultimately my answer, because remember, we take this value and we put it right here, so 2.22102. I just wanted to write it here so I can actually see, what was I trying to do? Find an approximation for y of 0.5. So the y value is 2.22102. So notice that we never rounded or truncated to the thousands place, because we're trying to get an exact approximation as possible, right? We're trying to get the best approximation possible, so we're not going to round. And I did obtain these values with my graphing calculator, but we'll see that we typically don't do this many repetitions, probably just 2 with some smaller numbers. In this next example, we've been given dy dx is x minus 2 with y of 0 is equal to 5. And we're asked to find an approximation for y of 0.8 using Euler's method with 2 equal steps. Alright, so in this problem I have not explicitly been given my delta x, and we have to calculate it. So if I want to get from an x value of 0 to an x value of 0.8 with 2 equal steps, that means I have to go up 0.4 every time. So my delta x is 0.4, right? So essentially we're just taking where we want to be minus where we were and dividing by the number of equal steps we want to take to get there. So notice that I filled out my delta x as 0.4 every time. And I filled out my horizontal row. That's going to be the same every time. So x, y old, delta x dy dx is the equation x minus 2 this time. So this time it's just dependent on x, but know that it could be dependent on both x's and y's. And then my formula here is still the same. So y new is y old plus dy dx times delta x. And I have filled out my starting value. X value is 0. My starting y value is 5. And then notice that I filled out my x values to increase by the change in x, right, delta x, every time. So 0.4 and then 0.8. So ultimately we're looking for an approximation for y of 0.8. We're looking for this value here. So my first dy dx, my first slope is x minus 2. Well, my first x is 0, and 0 minus 2 is negative 2. So we can see we're going to have 5 plus 0.4 times negative 2. So this is negative 0.8. So 5 plus negative 0.8 is positive 4.2. So now that's my y old for the next row, so 4.2. And now I need to find my new dy dx based on my new x. So my new x is 0.4. And 0.4 minus 2 is negative 1.6. So now we're looking at 4.2 and then plus 0.4 times negative 1.6, which is 3.56. And that is my approximation for y of 0.8 using Euler's method with 2 equal steps, so 3.56. So this is exactly the type of problem that would be on a test that does not allow a calculator, because you really only have to do one decimal multiplication here to get out this simplified answer, right? It wasn't as crazy with as many repetitions as the last one. So when a lot of repetitions are used with the smaller delta x, we usually go to computer programming software to solve for higher and better approximations. So it's not really something we tediously want to do by hand, only when the numbers are nice and small. So there's a part B to this problem. Now we're going to solve the differential equation dy dx equals x minus 2 with initial condition y of 0 equals 5, and then we're going to calculate y of 0.8 exactly. So we can do this because this is a separable differential equation. So we have dy dx equals x minus 2. So dy equals x minus 2 dx. And we can integrate both sides. On the left, we're going to have our y. On the right, we have x squared over 2 minus 2x plus c. And our initial condition is y of 0 equals 5. So y of 0 equals 0 squared over 2 minus 2 times 0 plus c has to equal 5. So in other words, c is 5. So I will just go ahead and bring that over here. My equation, my solution with this initial condition is y equals x squared over 2 minus 2x plus 5. So this is the exact solution. So if I want y of 0.8, I can substitute 0.8 into my x values. So I'm going to have 0.8 squared over 2 minus 2 times 0.8 plus 5, which equals 3.72. So y of 0.8 is exactly 3.72, and using our two-step Euler's method approximation, we said y of 0.8 was approximately 3.08. So that's not too far off for using Euler's method with 0.4 as my step size and only using 2 approximations as opposed to solving the differential equation. But again, you might be thinking, well, this wasn't too bad to solve and just substitute in, but some of our differential equations are not solvable, as in they're not separable, and we don't have the strategy to do so. So to find approximations on the exact solution curve, we need to use Euler's method.
Alright, last example of Euler's method types of problems, so a little bit different. Assume f and f prime have values in the table. Use Euler's method with 2 equal step sizes to approximate f of 2.6. So let's kind of take a look at what's happening. We have these x values. We start with 3, and then we jump to the next x value, 2.8, and then 2.6. So we can see that our change in x is going down by 0.2 every time. Alright, so just keep that in mind. So we're just analyzing this first table. And we have the derivative f prime of x. Well, that's like having dy dx, right? So we have dy dx, or f prime of x, at 3, at 2.8, and at 2.6. And we have f of 3 is 1. So that's like our initial condition, right? So I have, when I plug in 3, I get out a 1. And what I'm asked to find ultimately is an approximation for f of 2.6. So first I have to find an approximation for 2.8 and then an approximation for 2.6. So it's like I have to fill out the rest of this table. So now to do that, I'm creating on the bottom, right? So this part right here would be like the question. What I'm creating on the bottom is I'm just going back to habits, right? So if we see Euler's method, here's what we need to do is find x, y old, delta x, dy dx, and then compute that y new. That's what we're going for. Alright, so my starting x value was 3, my starting y value was 1, and my delta x this time is negative 0.2 because I'm going down 2 every time. So that also shows what's happening to my x values, right? 3, 2.8, and 2.6. So my dy dx is also my f prime of x, right? And f prime of x, or f prime of 3, was 0.4, right? So f prime of 3 was 0.4. So that's the slope that goes here, right? So now I'm going to compute 1 plus negative 0.2 times 0.4, which ends up being 0.92, because this is 0.08, but it's negative, so I'm subtracting that from 1, so 0.92. Alright, so that now goes right here. So that's my approximation for what's going on when x is 2.8 on f of x, right? Because y equals f of x. So this is 0.92. And then now I can find f prime of x at 2.8. So I was given f prime of x at 2.8 is 0.7. So now we're computing 0.92 plus negative 0.2 times 0.7, and that ends up being 0.78. So this is 0.14, right? That's being subtracted from 0.92. So 0.78 is my value, right? So If I plug in 2.6 into y, which is f of x, that's my approximation, is 0.78. So that is the value that I was trying to find. So this is an example of being given the information in a different way, right? We shouldn't always just be used to, oh, got it, it looks like this, do this. We might be given our information in alternate forms. And then this is also an example of when delta x is a negative value.